Now we're going to modify the last example, and let's do this by increasing so we'll have 10 degrees Fahrenheit of superheat. And we'll have 10 degrees Fahrenheit of subcooling. Now, when it says this, sometimes what people are, they're confused by this. So this 10 degrees refers to this distance. This was your delta T of 10 degrees Fahrenheit. And similarly, the 10 degrees of superheat so it isn't 10 degrees Fahrenheit, it's we're changing that value by 10 degrees. So if I look at this, H4 is equal to HF at 100 degrees Fahrenheit minus 10 at 90 degrees Fahrenheit. And so that's equal to 28.7. H2, and here what I had to do is go in the tables and interpolate between the saturated values and the superheat values because we didn't have a value of minus 10 degrees Fahrenheit in the tables. So I thought I would show you this just to remind you how to interpolate. So it's 0 degrees Fahrenheit minus 10, which is what we want, minus 20. So this is in the saturated tables. This is the lowest value in the superheat table, so I have to interpolate between them. And the enthalpies there, H at 0 degrees was 77.7, 77.9, 75.1. If I look at this difference, it's 2.8, and we're halfway between that. So if I take 1.4 away from this, we come up with 76.5. So that becomes the enthalpy value at state 2. And so Qn is equal to 76.5 minus 28.7. Qn is equal to 47.8. And now I need to find the H2 in H3. So I found H2. I did the same thing in S2. Doing it the same way is 0.1742. So you can do that, but I have to find S2 the same way I found H2. S3 is equal to S2. P3 is equal to 125 psia, the nearest table values. And with that, I have that H3 is equal to 96.6. And W net is equal to 96.6 minus 76.5 is equal to 20.1. And the COP is equal to 47.8 over 20.1 is equal to 2.4. So the COP went down. It was 2.77 originally. Now it's 2.4, so it went down. The Qin increased, but the W net increased faster. So before it was 15.89, and now it's this. So it increased faster, driving down the COP. And so that was the effect of this, but it makes for a safe operation in terms of we're not having flashing through the valve, and we don't have any liquid going into the compressor. And what we're going to look at now, we'll look at some of the components just to give you an idea of what they look like typically. So let's look at the heat exchangers. There are two heat exchangers. And for the condenser, it'll often be a shell and tube. such as in figure 6.8b. So we've looked at shell and tubes, and basically you have your coolant go through the tubes and the refrigerant passes over the tubes and it condenses. However, on small units, we don't have this. So this would be typically for large units, you might use water for cooling, something like that. If I have air for cooling, if air cooled, then I could have thin tubes. And we'll look at that in just a second. So it depends on the cooling medium. So if I have liquid as a coolant, then I'm going to have a shell and tube, thin tubes. And for your home refrigerator, if you look at it, you might just have plain bare tubing. And so that could exist. And then for the evaporator, so the refrigerant evaporates in the thin tube. And now we're going to have the challenge of my drawing of sketching a thin tube. So let's see what happens here. And so what happens with the fins, which you may remember, is I have something like this that goes around. Actually, I'm not going to see that. So this is one fin. I never claimed to be a good sketcher. You can say I'm verifying that right now. So what happens is these fins are attached to the tubes. They're attached fairly closely. And the reason from a heat transfer perspective is that we have Q dot is equal to the overall coefficient of heat transfer times area times delta T. And what the fins do is they're increasing A. So the fins increase the surface area. And so what happens is the refrigerant is in here, and then I have air flowing over this, and so I have a greater area. And if you look at HVAC compressors that are outside, that compressor unit outside, if you have central air, you'll see that the fin tubes, there are a lot of little fine fins on that tubing. So this has been developed to an art. Now let's say I want to look at the expansion valve. So the expansion valve is interesting in, it's figure 16.7 in the text, and we'll show you how it works. Thermostatic expansion valve. And so what happens is this regulates the superheat. And you look at figure 16.7 in the text. For a better drawing, for a less good drawing, we'll have the following. So I'm going to have the thermostatic expansion valve. Now the real challenge is I sketched it, now I have to sketch my sketch. So we're increasing the risk of things going awry here. And this is the figure going in here. The problem with doing this in real time. And so here's the evaporator. So this is the evaporator. And let's say I know for R12 at 0 degrees Fahrenheit, the pressure P is equal to 23.8 psia. At 10 degrees Fahrenheit, P is equal to 29.3. So at 0 degrees, so now I have my refrigerant coming in. I'm going to have a spring here. So there's a spring. This is why you need to look at the sketch. The spring, and it's attached to a valve. So I have a valve here. So this valve will move up and down and allow the refrigerant in. And what we wanted is we wanted this at 0 degrees Fahrenheit. So now the liquid is bubbling away and we have 0 degrees Fahrenheit. So I have 0 degrees Fahrenheit as it evaporates. At some point, all the fluid has evaporated and it starts picking up superheat. So let's say here it's 5 degrees Fahrenheit, and here at the end it's 10 degrees Fahrenheit. And how did that happen? So what happens is here the pressure is 23.8 psi. I'm going to have the spring provide 4.5 psi of pressure. And now what the thermostatic expansion valve does is it has a little bulb here filled with a refrigerant, and it goes up here, and this is at 29.3 psi. So what happens is I have the same refrigerant. I have a bulb attached here. Since this is at 10 degrees Fahrenheit, it'll be 10 degrees Fahrenheit in here, and the pressure associated with that is 29.3. So I dialed in this spring pressure so I can adjust the pressure, and so the 0 degrees provides this, I have this, and everything's balanced for 10 degrees Fahrenheit. And so everything is fine, but your cooling load changes. So what happens, and what makes this so nice, is it's a very stable control system. So now let's say Q dot in decreases because you've cooled down the food in the air-conditioned space. So we're going to have Q dot in decreases and superheat decreases. So the superheat decreases, and then what we call this is P3, so I call this P3, this is P2, and this is P1. Just so I have these pressures, so I can refer to the pressures. And so what we look at then is that if the superheat is less, then therefore P3 goes down, and P1 plus P2 is greater than P3, and the valve closes a little. And so when the heat increases, so I open the refrigerator door, I put stuff in, whatever's going on, Q in increases, so the opposite happens. So if I have Q dot in increasing, then the superheat increases. And P3 goes up. So if momentarily this went to 12 degrees Fahrenheit or 13, 14 degrees Fahrenheit, then this pressure would be greater. P3 is going to be greater than these two, and it's going to push to open the valve up more. And valve opens. So I'm not the only one doing homework on this, and let's look for homework. 16.3 star, 16.5 star, 16.7 star.